Okay, so hello everybody. I'm really excited to have Roy Schwartz here with us. Roy recently joined the staff here in the Hebrew University, and today we'll talk with us about green NLP. So Roy, the stage is yours.
Thank you, Elad, and hi everyone. I'm really excited to be here. It's my first time speaking here since I came back, so it's quite an exciting moment. For those who don't know me, my name is Roy Schwartz. I just started here as a faculty, but I was actually here until 4 years ago, where I did my both undergrad, master's, and PhD. Today I'm going to be talking to you about green NLP. I'm going to explain what it means and give a few examples. I would like to say that please feel free to jump in at any moment if you have questions or comments. I have the chat open, but it's going to be hard for me to pay close attention. So if anybody wants to write something on the chat, so maybe every few minutes I'll stop to ask them their questions and someone can read them out loud. Let's begin. Sorry. Okay, so the field of natural language processing, or NLP, has seen an enormous growth in the size of state-of-the-art models. And what we're seeing here is a plot that starts in early 2018 or late 2017 with the Elmo model that had roughly 100 million parameters. And about a year ago, Microsoft released a model called TNLG that has 17 billion parameters. So over 170 times larger than that previous model. And we shouldn't stop a year back, but a few months later came GPT-3, which was 10 times larger, and then TNLG, so about 175 billion parameters, so about 1,700 times larger than a model just 2.5 years back. And this is a very exciting trend in many ways, because it allows us to push state-of-the-art in NLP to new levels. Things that we thought were completely beyond our reach are now solved by these technologies. But at the same time, this trend raises a few concerns. The first is that models are becoming more and more expensive, obviously. There are some estimates of the GPT-3 model that I just mentioned talk about more than $10 million to train just a single model. And obviously, as you can imagine, us in academia and also pretty much and nobody that doesn't work in the very big companies can afford to do this type of research. And kind of the question gets asked, who gets to decide what are important research questions and who gets to set the agenda for our field? The second potential problem is about the consumers of our technology, because we're generating models that are very big in terms of space that they require and computational memory that is needed to run them. So it's not necessarily easy or possible for a simple startup or some organization to take this technology and use it. So, are we generating technology that's good for our internal benchmarks, but not really helpful for anything else? And finally, when we increase the size of our models in such an exponential manner, and training these models takes so much computation and power, this is starting to raise the question of whether we're seeing an environmental concern, or at least a potential one. So there was this work by Strubel et al. From UMass last year, or a year and a half ago, that showed that state-of-the-art neural architecture search method consumes as much CO2 as 5 cars would in the course of your lifetime. So combining these three potential concerns, we released last year a document called Green AI, myself and partners at the Allen Institute for AI, with some help from Greta. And in this document, we talked about the rising cost of AI and this trend when the problem that I just mentioned. And we proposed two paths forward, how to mitigate some of these concerns. The first is to enhance reporting of computational budgets, basically to add a price tag to scientific result, which would allow us to get a sense of how much compute is required to get a given result, and allow us to make fair comparison between different scientific results, in particular those that use different budgets to generate. And the second goal is to promote efficiency as a core evaluation for NLP. So basically, if today most of the field is driven towards getting state-of-the-art results in terms of accuracy and getting another epsilon on the accuracy or related measures is the only thing that matters, we propose putting more emphasis on how efficient the method is. And when we talk about efficiency, we're talking about efficiency during training or during inference or even during model selection. That is things like hyperparameter tuning. And we propose to combine it alongside accuracy, obviously not to replace it. Now, in this talk, I will talk about these two goals and try to explain a bit what they mean and dive a bit into some of our recent results on each of these. Now, before I start, I want to say a very important thing, that we don't try to argue that big models aren't important. Big models allow us to push the limits of the state of the art. In many cases, these large investments by typically big companies end up saving compute for others because they release the pre-trained models. And in fact, there's some works that even shown that large models are potentially even faster to train. So when you go bigger, your training time actually goes down. But at the same time, these big models have concerning side effects in terms of inclusiveness, adoption, and environment, I think that I started with. And so our result, again, is not to push them aside altogether, but try to mitigate these side effects. And this is what I will be talking about. So before I begin, any questions so far? Great. So here's the simple outline of this talk. We're going to talk about, again, the two main components that I mentioned earlier, to do enhanced reporting and to do more efficient processing or computation. So let's start with the first part of enhanced reporting. And with this motivating example from work from Reimers and Gurevich a few years ago, the premise of this work is that they started by taking a particular paper that tried to present a model, let's call it model A, and argue that this is a good model. And the way that they did that, they said, okay, let's take some baseline model B, and they got a better F1 score than the other model, which is something that we typically see in NLP and in machine learning models in general, in machine learning papers in general. And this type of comparison, taking two models and arguing that one is better due to just getting higher results. And what they did was they took these two models and reran them several times with different random seeds, not changing anything in the architecture, not even changing the hyperparameters, just running them again and again with different random seeds. And what you see here on the right side are two histograms of the results of the blue model on the left-hand side and the green model on the right-hand side. And as you can see, the original conclusion arrived by the authors of the original paper that the blue model is superior doesn't seem to be very accurate. If any, what we're seeing here, if any, the mean of the green line is somewhat higher than the one of the blue one, and also the standard deviation is smaller. So in fact, if I would have told you which one would you prefer to use for your task, I think most of you would actually prefer the green one. Another example from the task of language modeling. In this task, the details are not that important, but we measure the success of a language model by measuring its perplexity. So lower numbers are better. So on the top two rows, you see performance on some benchmark called PanTreeBank of an LSTM, which is a typical tool that used to be very popular in NLP until very recently. And we see results around low 80s or so, which is considerably lower than the state of the art that you see at the bottom of this table, which is about around 60. So again, the initial conclusion would be that LSTMs are not competitive for this test. They're significantly underperformed by more recent models. But then Melissa et al. Did basically the same idea. They carefully tuned an LSTM model running 1,500 trials with different hyperparameters this time. And they were able to show that with LSTMs, you can actually get roughly state-of-the-art results on this data set. So again, the same question we can ask, what is the fair comparison here? Are LSTMs, is the true performance, quote unquote, of LSTMs in the 80s or is it in the 60s? An important question that is not answered by this paper is what would have happened if we would taken any of the other models on the top of the table and run the same hyperparameter search on them. But something seems to be lacking here in this comparison anyway. So to summarize these two results, we think that maybe just asking whether model A is better than model B is not a fair comparison. And maybe what we should be asking is whether model A is better than model B given some computational budget. So a simple way to take budget into account is just to plot something that looks like this. You can, on the x-axis, we see some measure of the budget. Here we see the amount of floating point operation that took to train a given model. And on the y-axis, we see some measure of performance. In this case, some measure of, on the glue data set, we compute the glue score, and basically higher is better. And we can see that as you go to the right, obviously your performance goes up and your computational budget goes up as well. And maybe a good comparison is to when you want to argue that your model is better. Here we have a paper from last year that presented a model called Electra. You see that the red line is always on top of the blue line, which is the baseline, which is something that gives us a better understanding of the potential usefulness of a given model. And so here I want to talk a little bit about work that we did in EMNLP 2019, worked with colleagues from the Allen Institute for AI and at the University of Washington. So we proposed a method to present an even more accurate representation of the given performance of a given model. And our assumption is that we run a set of experimental experiments and get some results. These could be different random seeds or different hyperparameters. And the typical thing we would do is we would take the max of these results on the development set and report it along with the corresponding test result. But now we say, I mean, okay, so it's interesting to see what happens if you have n experiments and you can take the best one. But what happens if you have a smaller number than n? Say you have k, which could be 1 or 2 or n divided by 2 or whatever. So let's define v star k to be the maximum of taking the first k experiments. And so this is, you could say that, okay, so let's just take the first k experiments and just report them and generate the same plot that we generated yesterday. But this has some randomness that goes into this because who says that the first k are the most representative? So what we proposed is a different measure called expected validation performance. And this is a very intuitive measure, which basically says we want to compute the expected value of v star k for a given k. So what does it mean? If k equals 1, we basically take the mean of all our experimental results. Basically, what would we expect to get if we run n experiments, average them, and this is the basically expected result that we get for if we had a budget of 1 run. Similarly, if we had a budget of 2, this allows us to do 2 runs. So we take they take each pair of experimental results and return the mean results there. And obviously, if k equals n, this results in just the maximum value because we run everything and just take the highest value. So what does this give us? This gives us the ability to plot a chart that tells you very accurately how much are you expecting to get if you put this amount of work into your model. Basically, if you run this amount of experiments. So let's see this example here. what we see here is sentiment analysis experiments on a dataset called SST5. So on the left-hand side, we see, on the y-axis, sorry, we see the expected validation accuracy, basically the result of the measure that I presented earlier. And then on the x-axis, we see the number of hyperparameter assignments. So as we go to the right, we basically have a higher budget. And as we expect, model performance would go up. So what we see here is a comparison between two models. The red line is a logistic regression model, and the blue line is a convolutional neural network. And an interesting thing we can see here is that this plot is basically can be broken down into two pieces. If you have a budget of about up to 10 or 12 hyperparameter assignments, you're better off using the logistic regression. This model is potentially more stable. It will get you initially a higher result. And if you have a small budget, this is what you should be going for. Alternatively, if you have a higher budget and you can afford to run multiple experiments, a convolutional neural network seems to outperform the logistic regression. Any questions so far? Cool. Okay, so let's talk a little bit about the properties of this measure of expected validation performance. An important property is that this measure does not require running any experiments. This basically says that if you run n experiments, we will plot everything that goes between 1 and n. We don't ask you to run anything new. Just use your current results to get a better estimate of how your model will perform under different budgets. Another interesting property is that this measure is more comprehensive than what people usually use. Most people would either report the max result, basically taking the highest value of each of their experiments, or the average result, which is what you would expect if you would just had one run. Now, as you can see, our method generalizes over these 2 points. And in fact, the max is the right-handmost point, and the mean is the mean with EA is the left-handmost point. And we also provide every value in between. So not only if you had a budget of n or a budget of 1, what happens if you have a budget of 2 or 5 or 10 or whatever, everything between 1 and n. And we have code to generate these plots. If you're interested in your upcoming experiments, you can feel free to do that. Okay, so to recap this part of our reporting, we talked about budget-aware comparison. Basically, we want to be aware of how much budget we put into a given experiment, and to be careful not to make the wrong conclusion because we are comparing basically apples and oranges, or two models that had a different amount of computation put into them. And maybe this is the reason why we reach certain conclusions than on others. And we presented expected validation performance that gives us an estimation of the amount of computation required to obtain a given accuracy. And so to talk about a few open questions that we have with regards to reporting, and I think maybe a very exciting question is how much will we gain by pouring more compute? Basically, when we talk about expected validation performance, we're saying, say that you already ran an experiment, we can tell you how much would you expect to get if you only ran n divided by 2 or divided by 3. But what happens if you want to predict the future and say, what happens if I have 2n or 10n or 50n? Which model should I be investing in? And another key question that is still out there is, what should we report as our computational budgets? So I gave you a couple of examples of thinking about the number of experiments that you run or the number of floating point operations. You can also think about training time, the amount of energy being released, the amount of money it takes to train these models on the cloud, the amount of carbon that's being released, and so on and so forth. And getting to, and I don't think there's a right answer here, but at the very least, trying to make these methods simpler to implement and to use in your experiments is an important question to promote these topics. Okay, so before I go on, any questions so far?
Yes, I have one. If we are thinking like a big company like Google, then usually what they want to do is to give a trained model and use it for people to use. So obviously they will want to get the maximum, the best model they have. So I mean, why should they use other comparisons if they only want two people to gain the best of their model?
That's a good question. So first of all, I'm not a Google employee, and I don't think many of you are either. And I mean, we're trying to make science. And for me, in many papers, you scientific papers, quote unquote, you see scientific claims that try to say, I have this idea that I think works well, and this is how I prove it to you that it works well, by making comparison and saying that I'm better than some baseline. And what we're trying to argue that this claim is not necessarily valid if you don't take into account the budget. And maybe the reason that you're seeing an improvement is because you just put more money into it or more compute. And I mean, again, so even if your goal was just to generate the best model, I mean, how would you know that you're taking the best model? And if you used another architecture, you would get something better. So that's basically the argument we're trying to make. Other questions?
Yeah, I have a question. How can we actually enforce it? Because, when people do hyperparameter search, you can't really know what they have already tried. And I think even like personally, when I try different hyperparameters, many times it's not like I do a complete grid search. I just try various things and not always I keep track of everything that I tried. So how can you actually report it in practice?
That's a very good question. And I'll give you several thoughts that I have. First of all, I try to give credit and have good faith in people. So, I mean, you can also ask the same question of how can you trust people that are not faking results? I mean, we're very much incentivized to get good results. So why shouldn't I take my 89% and say that it's 92? And, it's, I mean, you can say that you can enforce it by people releasing their code and everything, but I mean, it's not, I mean, we live in a community that we need to trust each other. And if someone says that they ran 10 hyperparameter experiments, I want to trust them and not assume that they run 100. But I think you're touching on an important question. I mean, how can we incentivize the community to be more open about it? And I think this is the question that I've been thinking quite a bit recently. And we have efforts that we work with conference chairs. Actually, we just had a meeting yesterday with the chairs of EMNLP, which is one of the biggest NLP conference, and trying to get them to change the call for papers to encourage both reviewers and authors to do a better job at reporting and to do a better job at evaluating papers that report or don't report. So, I mean, we're trying to work by giving presentations like this and convincing researchers of the importance of this, and trying to work from bottom up by convincing the conferences and workshops to use these methods. But I agree, it's a long battle to get everyone to adopt it. Did this answer your question? Cool. Anything else? Cool. Okay, so let's continue to the second part of this talk. After we're talking about enhanced reporting, we can talk about the other goal for the Green NLP agenda, which is developing efficient methods. Now, when we talk about efficient methods, we can talk about various things we want to make efficient. We can talk about different parts of your pipeline, starting from doing inference through training a model and all the way to model selection, or basically the process of selecting the architecture via things like hyperparameter search. But we can also talk about what are we measuring? What are we trying to make more efficient? And there's also several things that are not necessarily aligned, things like space, trying to reduce the number of parameters, trying to reduce the number of the amount of time it takes to do any of these operations, or trying to reduce the amount of energy. And again, I will be talking about methods that touch on some of these aspects. In many cases, it might be contradicting. For instance, you could think about a method that trains for much longer time but results in shorter inference time. So we can think about ways that or a very slow model selection methods, but one that finds a model that trains faster or that runs inference faster. So again, these things are not necessarily aligned in their goals, but I think it's important to know the options and ideally find something that does combine benefits for all of these approaches. So let's talk about efficient inference. That's probably the most widely studied topic. And I think the main approach for making inference more efficient is to take a large model that's been trained, basically our baseline model, the full model, and trying to generate a smaller version of it. So a few examples that unfortunately I won't go into too many details, but those are interested are welcome to reach out, and I'll send you some notes about them. First thing is model distillation, and here we're talking about a parent, student, teacher approach, where we train a big model and then train a smaller model that tries to imitate the bigger model. And this smaller model results in a smaller space, but also smaller, shorter inference time and smaller amount of energy. Another similar approach is pruning, where we train a dense model and trying to learn a sparse version of it. Again, starting with something big and then converting into something small. Here, again, we potentially save space. And if we do the pruning in a structured way, we can also save time and energy. And finally, we can talk about quantization, which talks about training a model with full precision, floating point precision, and learning an equivalent version that uses a less precise floating point number. So all these share in common, again, this theme of starting big, training a big model and then trying to convert it into a smaller model, which relates to the point that I just mentioned in the previous slide, that again, here we're not saving anything on training or on, we actually make training longer and which take more resources because we do something on top of the standard training, but the resulting something that is more efficient at inference time. And sometimes this is what we need. And a couple of other methods to do space to be more efficient in terms of space, which I will again very briefly touch upon. One is weight factorization. Basically, we take a matrix, a large matrix, and learn to decompose it into a product of two smaller matrices. We can replace some of our big matrices like in this way and result in a model that performs roughly the same and takes roughly the same amount of time, but is much more space efficient. Another simple but very effective idea is weight sharing. Basically saying if we have a large model with many layers, for instance, we can just tie some of the weights and say that layer 1 is equal to layer 2, for instance, or usually in language, we would say that the first layer and the last layer would be equal. And this results obviously in saving quite a bit of space because we only keep one copy of these weights. When we talk about making model selection more efficient, we typically talk about early stopping. Basically, if we run multiple experiments, we can run them in a way that we start by training all the models, and then we see which ones are most promising, and just stop them at this point until we continue, and then do this again until we reach just a handful of models which we train to convergence. This basically means that instead of running n experiments all the way through, we would be running just a few experiments all the way, and the other ones would be stopped much early on. And we have shown that this works not only for hyperparameters, but also for random seeds. This pointer might be relevant for those interested. There are a bunch of other methods that don't fall into these categories. There's methods that try to take models and by providing a better mathematical formalism, get something that's more efficient. One particular approach is to replace the dot product attention, for those who know what it means, with efficient alternatives. Another is to try to do an analytic solution to the backward pass. Basically, instead of doing a backward pass in neural networks, to solve it some way analytically. And there's also methods that try to use more efficient, they use the input more efficiently. Basically use smaller parts of the input, or use the input in a better way that allows us to save time, either during inference or during training. Yeah, this was a very brief overview. I assume that many of the details weren't very clear, but if there's any question, I'm happy to take it. And before I move on. Okay, oh, sorry. Okay, so now I want to present a work that we presented a few months ago at ACL. This was a joint work with Gabi, who is also just recently joined our school, Swaba Swamdimta, Jesse Dodge, and Noah Smith, all at the Allen Institute for AI at the time. So what we're presenting here is another method to make inference more efficient, in particular for time and energy and not for space. And our starting point is a graph that we've seen earlier in this talk. And what I want to take from this graph is the trivial observation that as models consume more resources, they become more accurate. And what we're trying to do in this talk is to try to enjoy the benefits of both worlds. Whether we can get a model that is as efficient as the most efficient model, but as accurate as the most accurate model. So this seems like something that would be quite useful. So let's see how we try to do that. So the key idea that we follow in this work is that there's variance in language utterances. So if you look at this simple example of example in the task of sentiment analysis, basically you want to predict whether these documents are positive or negative. You can obviously see that one is very easy to classify. It contains only 4 words. It's very simple, not requiring any significant processing. And the other one is much longer, contains expressions like, I can't help but wonder whether the plot was written by a Tradeoff or an award-winning writer. And obviously, it takes more processing and more effort to recognize that the second one is not a positive argument. So, and we use these 2 observations. The first, that models vary in how much how much computation they require, and that instances vary in how much computation they require to process them, and try to match the 2. We want to allow a model to run on an efficient model on easy instances, such as the number 1 in the previous slide, an expensive model on the hard instances. So basically, our assumption is that the given approach, that basically what's the baseline, what's typically being done in our community nowadays, is to just take the most expensive model and run it on all instances. We argue that you don't have to do that, and you can run a simpler and more efficient model on many of the instances and still get the same performance as you would. So let's see how it goes. So our model is a pre-trained BERT. If you don't know what BERT means, just assume just a standard neural network with multiple layers. And that's the standard way of working with it is to add a prediction layer at the end, which a classification layer which makes a prediction as to the correct label. So if this is our baseline, we want to work with a couple of, this is our baseline, which is the slowest and most accurate model. We can introduce a couple of other models by stopping earlier. Basically, because each layer adds another amount of processing into our model, we can stop earlier and make a prediction. And this would require a faster model because we're not running all the models, but probably one that is less accurate because models typically become more accurate as we go towards the end. And finally, we can think about a model that stops after a single layer, which would be our fastest model because it processes just 1 out of n layers compared to the baseline, but it's also probably one that's least accurate. So now that we've seen our models, the components of our model, let's see how our approach works at training time. We do the following. Instead of having one prediction layer, we add multiple prediction layers at various steps along the way, after various layers. And we start by running our inputs, and we train our model to make accurate predictions using all of these layers, all of these classification layers. So again, in training time, we would train the model by summing the loss of each of these classification layers and trying to make the model work well on each of them. And at inference time, we will do the following. We will start by running our input through the first layer. Then we reach our first output layer. So we make a prediction and we ask the model whether it's confident or not. If it is confident, we stop. We trust the model and we make an early exit. And that's why in this way, we saved a lot of computation. If the model is not confident enough, we'll continue by processing this input through these subsequent layers until we reach the next classifier. And then we will repeat the same process. And here in this case, the model is confident enough, so we make an early exit, but potentially we could go on until we reach the final layer where we would be equivalent to the original model.
How do you decide the confidence?
Sorry?
How do you decide whether your prediction, the confidence of your prediction?
That's a great question. I'll get to it in a second. So how do, exactly 1 second later, how do we decide whether to make an early exit or not? So we take the softmax label score of the model as our model confidence. Basically, the model returns already a softmax, which is a normalized score between 0 and 1. So for the most predicted label, you can take the number that tells you how confident the model is. We use a technique called model calibration, which for those who are not familiar, tries to encourage the model to align well with its actual predictions, meaning that if the model gives a confidence score of 70%, the chances that it will be correct is actually 70%, because in many cases the models are not really good at estimating their chances of success. And importantly, now that we have this confidence-based method, we can control the exit early process by using a single confidence threshold. So basically, if you give me a number, say 0.5 or 0.7 or 0.9, I can generate a method that will allow me to go either to the left or to the right in my speed accuracy trade-off. If the threshold is lower, this allows us to make earlier exits because we allow the model to go with its prediction even if the model is not confident enough. And if it's higher, we're more likely to go up and get a model that's more accurate but less efficient. Is clear?
Can I ask a question?
Sure.
The training is the same? I mean, it's just inference time that is different?
The training is almost the same. Let me go back. This is the training part. So you train. So this is how you normally train it. This is the baseline. You just run through all the layers and use one classification layer and make a prediction, always at the same place. What we do is add multiple classification layers, and at training time, you try to make them all work together by summing their losses.
But this decision of deciding whether you go to the next layers, it's not implementing during training time. This is only inference time.
Exactly. Yes. Other questions? Cool. So where were we? Okay. So this is our method in a nutshell. So let's talk a little bit about experiments. So we, again, without going into the details, for those who are not familiar with large NLP models, we take a model called BERT, and we add, this is a model that has 24 layers. So we add layers to in different places, 0, 4, 12, and 23. As a side note, I would say that we tried a bunch of other configuration and didn't seem to make a huge difference, but we obviously didn't exhaust the search space. And we experimented with 5 NLP datasets. 3 of them are text classification, basically getting a document and classifying into one of 2 or 3 different categories, and 2 data sets of NLI, which basically measures the relationship between the 2 documents, whether one document entails the other or contradicts it, or none of them. And as our baseline, we used 2 types of baseline. And the first one is the standard baseline, basically how we would typically do things, just run everything until the last layer and make a prediction. And efficient baselines, which train a single classifier, but stop earlier. Now note that this is, we can implement these baseline using our approach, but our approach is different because we train everything using all 4 layers. And here where our baselines use just 1 layer. So in this sense, they have some advantage because they can focus their efforts for one particular classifier, while we have to divide the attention between different ones. Okay, so let's look at some experimental results. So we first noticed that our baselines are pretty strong. What we see here, are 2 text classification data sets, and the green point is the standard baseline, the thing that we would typically be using. The red points are the efficient baselines. We see 3 of them. And for instance, if you look at the left-hand side, AG News, you see that the second red point there is almost 3 times faster than the standard baseline, while losing just 1 relative accuracy point. So again, what do we see here? I should have told you this earlier. On the y-axis, we see the accuracy of the model as a percentage of the full model. So 100% is our standard baseline of just training all the way through and getting a result. And so by losing 1 relative point accuracy, we're able to get 3 times faster, which is what we see on the x-axis. Again, this is the processing time, again, relative to the standard baseline. And on the other data set, we see that the decrease is a bit sharper, but still we can get models that are performing roughly okay while being 2 or 3 times faster. Now let's see how our approach does. What we see here are on the blue line is running our approach with different thresholds. So each dot is at a different threshold. So when you use the higher thresholds, you get typically higher accuracy and a slower processing time. But we see a very interesting observation that if you take the, can you see the mouse? Can you see it? So if you look at this point again here, this point gets about the same accuracy. Well, if this one was 3 times faster, this is 5 times faster. And similarly here, if you control for the amount of time, this is much higher. And similar results are observed for the other data sets as well. And results for the other 3 data sets, some of them look similar, others look the 2 bottom, we don't do much better than the baselines depending on the budget. But in general, the method does at least as well as our baselines.
Okay. Can you explain why you have different blue dots?
Sorry, again?
Can you explain again why you have several blue dots and not just 1?
So the blue dots represent different thresholds. So the left-hand side dot represents the threshold of 0, I guess, of always going with the most efficient classifier. And the right-hand side talks about 100%, or it's probably not 100, but maybe 95% or 99%, and everything in between. So this comes to illustrate what happens when you increase the threshold. Clear? Cool. So a few more words about our approach. So the first thing to notice is that there is no effective growth in parameters for the model. If you compare it to the baseline model that has, again, the 24 layers, we're just adding 3 or 4 additional classification layers, which are much, much smaller than the hidden layers. So effectively, it's this, we're getting for the same price, same parameter price, a model that allows us to do a more efficient inference. And similarly, because we're just training just a few more classifiers, training the model is not slower compared to training the full model. But what we do get is a single model that provides multiple options along the speed accuracy trade-off. And we can control it using a single parameter, the confidence threshold. So unlike our baselines that if you said, okay, I want a model that's twice as fast, and so I need to train a different model with a different classifier, so training time is roughly twice slow, we can control with just our single train model whether we want a model that's twice as fast or 3 times as fast or 4 times as fast, or just a model that's the baseline that is roughly as fast and as accurate as the single model. And the only caveat I would add here is that due to our implementation, we only implement this approach for batch size 1 during inference. This is because we have to make a decision for each instance individually. So this is in a way proof of concept, but there are simple ways that this can be extended to larger batch size that we left for future work. Okay, so to recap, we talked about efficient inference and we talked about efficiency in general and presented a method for efficient inference. And we based on our intuition on the fact that simple instances can exit the model early because they don't require much processing, while hard instances need to get more compute. We've shown that training is not slower than the original BERT model, and that we have one model that fits it all. And we can get using a single parameter that controls for the speed accuracy curve. Questions?
I have a technical question. Did you implement this branching, this decision of whether to exit early on the CPU or the GPU? Because if you implement it on the CPU, I can imagine that all this back and forth between the CPU and GPU can make you worse off, and you might be better off just running all the layers through the GPU.
We implemented on the GPU. We didn't test it on CPU. And again, except for the caveat that we ran inference with batch size of 1, there weren't any technical challenges in this respect.
So just one thing I'm wondering, you're saying the training is not slower, but potentially you can make the training faster if you imply this branching out during training somehow, right? So since on many examples you actually branch out, you only care what the higher layers are saying about the examples that don't branch out. Did you try anything like this?
That's a very good comment. Actually, I had a student, Yarden, I'm not sure if she's here now, that tries something similar. We couldn't really get it to work, but I must say I don't think we fully exhausted it. So this is definitely an interesting idea to try in future work. Thanks. Other questions? Let me look at the time. Okay, good. Okay, so taking a step back, let's talk about a few open questions that we have about efficiency. So one of the major challenges is to reduce the cost of training, in particular for these large models that I presented at the beginning of the talk. Models are becoming bigger and bigger and more expensive, and can we do something to significantly reduce the price of training them? BERT is one example of these models. Another related question is, can we do sample efficiency? Basically, train the model using less data. Obviously, if we use smaller amounts of data, we can train the model faster because each epoch is slower, assuming the model makes as much as it can from the smaller data set that it does from the larger one. And we have some initial work along this line. And a very interesting question is what makes a good sparse structure? Can we recognize these sparse structures in advance? Do we have to train the model all the way to reduce it to a sparse version, and so on? And finally, another very important question is what makes a good hyperparameter or random seed? Again, can we identify in advance our hyperparameters that will be more useful than others? I mean, there's kind of this common wisdom about things like learning rates or dropout rates, but can we build a more fundamental or more principled theory around them? And more importantly, or I don't know if more importantly, but asking a different question, can we study random seeds and know in advance whether one random seed would be better than others? And this might look like a potentially strange question to ask because it's just random numbers, but we have some initial results that show that random seeds affect two different things in our models. The first thing that they affect is the initialization of the weights, and the second is the order in which we traverse our training data. And we've shown that different orders lead to very different experimental results. So are some data orders better than others? And there's some research about this, but definitely more to ask about this. Okay, so to recap, I want to encourage you to think green and both show your work, meaning show how much computation you've used, and make a good and fair comparison between different models, and think about efficiency and not just accuracy. Before I wrap up, I want to say just a couple of words about myself, not related to this talk. I'm very interested in understanding the NLP developmental cycle, basically understanding the different parts of NLP models, which basically means studying the data sets that we work with, trying to understand what they contain, what do they tell us, what do they teach us during training, what do our tests tell us about the abilities of our models, and so on and so forth. And I'm interested in understanding what's going on inside models, and during the training process, we had some interesting work that finds equivalence between a family of neural networks and weighted finite state machines, but also various other works that try to dig deeper into the mathematics of both the representations of the model and the training process. And finally, the thing that I talked about here, understanding the meaning of our experiments, what happens when we get some experimental results, and does our comparison lead to actual differences between models? So again, I just started here recently, and my lab is growing. But if you're interested in, if any of this sounds interesting to you, please reach out and let's chat. And the amazing collaborators that and without them, I wouldn't be standing here. And thank you for your attention, and I'm happy to take more questions.
So thank you, Ray. Is there any more questions?
Yeah, thanks. Very, very nice work. I have a more kind of a conceptual question. You talked a lot about the importance of efficiency and the environmental impact of all these big models. The question is, don't you think maybe this is just an hardware kind of issue? Maybe, you know, computers back in the day took a whole room and consumed a lot of energy, and now we have on the phone or on our watch something that can do as much or more computation. So maybe we're just in an era where you know, training these big models is an issue because the hardware is not yet optimized, but in 10 or 20 years we can train these huge models on our watch, and this would not be such a big issue.
That's a great question, and I definitely think that one of the promising direction is to working on better types of hardware. But I think it's, I mean, if we, can you see the whiteboard here? If you think about the plot that I've showed you earlier that looks something like this, we're talking about the growth of 10x for the last 10 years in AI models. And Moore's law talks about 1.5 every 1.5 years or so. So, I mean, Moore's law looks something like this. So the models are becoming bigger and bigger, and we've seen this trend for about a decade or so in AI, and the hardware is unable to keep up with our experiments. So I agree that there's more to do here, but it definitely, I mean, we're running way faster. Yep. Other questions or thoughts?
Hi, can you hear me?
If you can talk a bit louder, that would be great.
Yeah, can you hear me?
Well, start and then I'll try to see if I hear.
Okay, you talked about the data representation early on, how you can use floating point value variables with less data, like using floating point operations of 16 bits or 8 bits instead of 32 bits, for example. But not all hardware is born the same, and some GPUs are more optimized for different types of data size, and some work better with sparser data, and some work differently. Is this something you researched during this, or is something for the future?
Yeah, thank you for your question. Let me repeat it to make sure that I heard you, because I heard you. I think I think I understand what your question. You were asking about quantization of the process of taking a full floating point and converting it into a smaller, with smaller precision to save space. And you asked about different architectures and how this affects them. Is this roughly what you're?
Yes. Plus, how can you take into account the GPU architecture? Because newer architectures are very different, and you can't really optimize for every GPU and for every network.
That's a very good question. I must say, I personally have not worked on these methods, so I'm not an expert in them. I do know that I mean, these operations are also being supported by companies like NVIDIA. So they're trying to, when they release a new generation of GPUs, it comes with basic support to do computations with lower precision. But I'm not a very good expert on it. And you're definitely right that things that you do for one architecture might not transfer very well to other architectures.
Okay, thanks.
Any other questions?
Okay, so Roy, thank you again. And
thank you, everyone.
See you here in our halls again. So, yeah. Goodbye.